Catalysts, process by which we can increase the reaction rate. Catalysis is a process of increasing the rate of a reaction. We add a substance to the reaction which causes the reaction to occur more rapidly. It does this by providing an alternate mechanism. Instead of going through the standard reaction mechanism, there is an alternate pathway that this reaction can take in order to reach the product. This alternate reaction pathway tends to have lower activation energy barriers than the standard process, which gives it an overall faster reaction. As we lower the activation energy, more particles have a percentage of energy necessary to reach the reaction process, either if we're looking at it from collision theory standpoint or from a transition state theory. Now, there are two types of catalysis. There's homogeneous catalysis, in which the catalyst is in the same phase as the reactants, and there's heterogeneous catalysis, in which the catalyst is in a different phase. Now, the catalysis process does not alter the nature of the reaction. The stoichiometry of the reaction is the same, and the overall spontaneity doesn't really change. What changes is the rate of the reaction. A catalyst can be transferred between steps in a mechanism, but must always be regenerated by the time the reaction is over. So the catalyst is not produced or consumed by the reaction. Therefore, it is not listed as either a product or a reactant. It is put into the reaction at the beginning and comes out of the reaction at the end unchanged overall. Typically, the catalyst is written over the reaction arrow. Now, a catalyst we can think of as the opposite of an intermediate in a reaction. A catalyst is used in the beginning and then reformed by the end of the process, where an intermediate is formed at the beginning of the process and then used up before the end. We can take a spontaneous reaction which is slow and make it a useful reaction by means of catalysis, by speeding up the rate. If we look at a reaction energy diagram like this, we have reactants on the left, products on the right. Looking at the blue line is our standard reaction process. We go from reactant to a transition state, which has a EA, activation energy, that is represented by the green arrow. This goes from the transition state down to products. The reverse activation energy, going from product to reactant, is represented by the gray arrow on the right-hand side. The overall change in energy of the reaction is the energy difference between the reactant and the product. Now, a catalysis process is represented in this case by the purple line that is underneath the blue line. The energy of activation for the catalysis process is represented by the gold arrow. This energy is less overall than the EA of the green arrow, which means that the energy needed to get through the reaction is lower. Note that this also has a two-step pathway. We've got two hills here. That's oftentimes the case with catalysis. It breaks the reaction up by a different mechanism. The reverse energy is the energy needed to go from product to reactant. This is represented by the charcoal dark gray arrow. See here that it is, once again, because this is an exothermic process, still higher than the activation energy in the forward direction. If we look at a distribution of particles as a mole fraction with a certain amount of energy, the uncatalyzed process is represented by the purple selection, the catalyzed process by the red selection, with the respective activation energies listed in purple and red. We see a higher percentage overall of particles which can pass the activation energy in the catalyzed process than in the uncatalyzed process. Now, homogeneous catalysis exists in the same phase as the reactants. Frequently, things like acids and bases are used as homogeneous catalysts, but we can also use oxidizing agents as well, for instance. If we look at an example of a homogeneous catalysis, the oxidation of tellurium by cerium, going from 1+ tellurium to 3+ tellurium, and cerium from 4+ to 3+. We use manganese 2+ as a catalyst. The cerium reacts with the manganese to produce cerium 3+ and manganese 3+. The cerium 4+ will react with the manganese 3+ and produce cerium 3+ and manganese 4+. The manganese 4+ will then directly react with the tellurium to produce manganese 2+ and tellurium 3+. The net reaction, because the manganese 3 plus and manganese 4 plus are both intermediates, which are consumed in the second and third steps respectively, is that manganese 2 plus starts and manganese 2 plus ends, so it's a catalyst, it's ignored. The cerium 4 plus, 2 of them on the left, the cerium 3 plus, 2 of them on the right, tellurium 1 plus on the left, tellurium 3 plus on the right. The overall reaction is the one that we wanted to accomplish. Heterogeneous catalysts occur in different phases from the reaction system. Usually heterogeneous catalysts are things like solids. They provide a surface for adsorption. Now, adsorption is different from absorption. Adsorption refers to something sticking to the surface, where absorption is being soaked in. Adsorption to the surface of a catalyst makes the collision easier to accomplish in an effective manner. An adsorption process will hold a substrate in a specific configuration, and in doing so makes it easier for another reactant to come in and hit it from a proper orientation. It also has the potential to weaken or break bonds in the reactant that is adsorbed to the surface of the catalyst. Overall, the process is referred to as activation of the substrate, where activation makes the reaction easier, and again, substrate refers to the reactant that is being used by the catalyst. After the reaction, desorption, or the opposite of adsorption, will occur to release the products that were created in the reaction. Oftentimes platinum, palladium, gold, or nickel will be used as heterogeneous catalysts because they contain empty d orbitals, which electrons from the reactants can occupy in order for the bonds to be broken or weakened. As an example, a catalytic converter in a car is used to catalyze reactions of isooctane to carbon dioxide and water, the reaction of carbon monoxide to oxygen and carbon dioxide, and the reaction of nitrogen monoxide to nitrogen and oxygen. All of this is used to clean up the exhaust coming out of the engine because it reduces residual octane, which might be in the gas fumes. It takes harmful substances like carbon monoxide and nitrogen monoxide and transforms them into clean air components like oxygen and carbon dioxide and nitrogen. Sometimes, however, a catalytic converter can catalyze unfavorable reactions. A lot of catalysts have this problem because their specific reactivity may allow them to catalyze reactions you don't want them to catalyze. In the case of the catalytic converter, it can convert SO2 to SO3. SO3, once formed, can react with water to make sulfuric acid. So if you're doing this, you can wind up getting sulfuric acid in your exhaust, which can eat away at the components of the vehicle. Catalysts can also experience what's called poisoning. Poisoning is a deactivation of the catalyst that occurs when a substrate sticks to the catalyst and does not let go. It blocks the site of the catalyst for other reactions that would normally come in and prevents the catalyst from being able to act on these. Usually poisoning occurs when you have some substance that is not being able to be acted on by the catalyst. In the case of a catalytic converter, like a nickel oxide converter, you can get poisoning by lead, which is one reason why lead is not used in fuels anymore, because it destroys the catalytic converter over time. If we look at an example of a heterogeneous process catalyzing the conversion of carbon monoxide to carbon dioxide with the production of an oxygen atom, overall the process is a cyclic process. We start with the adsorption on the top left, where the oxygen and the carbon monoxide will stick to the surface of the catalyst. Moving to the right, then we have activation. In this instance, we're breaking the bond between the two oxygen atoms in the oxygen molecule, freeing up one of those atoms to be bonded to the carbon monoxide near to it. We then move on to reaction, where the carbon monoxide reacts with the free oxygen atom to make carbon dioxide, leaving a residual oxygen atom behind. And then we move on to desorption, where both the residual oxygen atom and the carbon dioxide molecule leave the catalyst and move on. Generally, adsorption occurs because the substances have a relatively high attraction to the catalyst. The products that are produced from the reaction will often have a low affinity or low attraction to the catalyst, and so won't stay on it very long and will wind up leaving opening the catalyst up to continued reaction with new molecules of the substrate. Enzymes are a specific type of catalyst, particularly heterogeneous catalyst, which serve as biological catalysts. They are used ubiquitously throughout biology. They're in all of your cells, and they catalyze a variety of different biological reactions. They're comprised of proteins, and they contain a reaction component that's called an active site. This is where the chemistry occurs in the enzyme. They use a variety of different chemistries to do different reactions. Generally, an enzyme will be specific to a single reaction or a class of reactions, rather than being something that's open to multiple different types of reaction. In an enzyme, as before, the reactants are referred to as substrates. A substrate generally has an affinity or a liking for the active site of an enzyme. It has a chemical attraction to it. The reaction occurs because the enzyme will activate the substrate. Generally, enzymes are able to run in very mild conditions with pH about 7, 37 degrees Celsius body temperature. They are very highly efficient processes, much more efficient than most of our man-made catalysts are able to accomplish. And they function to activate because the substrate transition state has a higher affinity for the active site than the substrate itself does. So while the substrate is attracted to the active site, the transition state of the reaction is even more attracted to the active site. We can actually use this process to create inhibitors for an enzyme, which have a resemblance to the transition state of the substrate the enzyme acts on, but are not active chemically, and so they block up the active site and quote-unquote kill the enzyme, keeping it from being able to catalyze more reactions. If we look at a process by which an enzyme works, first the enzyme and the free substrate will be attracted to each other in adsorption. The free substrate will be attracted into the active site, from where it will then proceed to change as it proceeds along the reaction pathway to the transition state. Because the transition state has a higher affinity for the active site than does the free substrate, the enzyme is able to make the transition state occur more effectively with a lower overall energy. The transition state, if we see here in this crude example, is better fitting into the active site than the substrate was. From here, the reaction continues to proceed until you reach product. After you reach product, the products are released by the enzyme, freeing it up to continue the process. Now, these sort of heterogeneous catalysts, particularly enzymes, are what we call zeroth order kinetic processes. They are independent of the concentration of substrate because depending upon how many enzyme protein molecules you have, the reaction rate is limited. Each of these molecules can only take one substrate at a time. Once all the enzymes are full, any additional substrate to the system will not increase reaction rate anymore, because they'll just sit around having to wait for the next available active site to be open for them to go in. So overall, a process that is enzymatic will be zeroth order rather than first or second order in its kinetics.